Today's soil mechanics lab is going to be about the triaxial test. And this is another test where you could get a shear strength value for cohesive soil, so meaning like silts and clays, or cohesionless soil, sand. So it can be performed on both tests. Why I said here unconsolidated, undrained, because that's what your lab report is going to be required, or the data that you will get will be for unconsolidated, undrained test. But there are many types of triaxial tests, and I'll discuss them in a little bit of detail. But basically, if you remember the last lab, we talked about the shear box test, which will enable us to get a shear strength measurement for soil. You had a predetermined plane of failure. So basically, you failed the sample along a pre-specified plane, predetermined plane. But in a triaxial test, you allow the sample to fail under the plane that it wants to fail. So it wants to fail under a certain plane, it will fail along that plane. And also, Casagrande developed this test, and what he was trying to do is have a little more control on the drainage conditions that you have and on the pore water pressure measurements that you can get throughout the test. Although we know that you can run a direct shear test slow enough that you have drained conditions. But here there's more precise measurements during the consolidation phase of a triaxial test and during the shearing phase of a triaxial test. So you have control over the drainage conditions and pore water pressure measurements inside the sample. So this is a basic setup. You have here a chamber that you put your soil sample in, and we'll go into this in detail in a bit. Here you have water, de-aired water all around your sample, and then this is pressurized. So basically it applies a consolidation or a consolidating stress, sigma 3, minor principal stress, all around your soil sample. So it would be better if I would take it right here. And what I have is, let's say that this is your soil sample. And let's imagine that you have here a drainage valve, and this valve can either be open or closed during both phases. And here, let's say you have a gauge that will measure pore water pressures. So basically you have two phases in a triaxial test. You have first the consolidation phase in a triaxial test, and that's where you apply this sigma 3, minor principal stress. And if you would imagine that this is in a chamber with de-aired water, and then you can either, in this phase of the test, you can have the drainage valve open or closed, and then in the second phase, you will apply the major principal stress and fail the sample. And you can also control the drainage conditions during failure. And if we go down here and just take a quick look, this is all, I've mentioned this stuff before, but I'll go over it at the end just quickly. Here you have the main types of triaxial tests. So if we were to look at an unconfined compression test, this test, basically you have your soil sample and you don't have a chamber around your soil sample in an unconfined compression test. Basically, you only have air around you, and then you apply the major principle or the shearing stress, and you fail the sample. And your Mohr circle would look something like this. It would start at 0 because our sigma 3 is 0. We don't have any confining stress. And then this will be the major principal stress. And this will be your failure envelope. And here you would have an unconfined compression strength. And it's not really, in a sense, a triaxial test because you don't have a triaxial chamber, but it's one of the tests that you can do. It's an unconfined compression test. Now, if we move more into what we're talking about, an unconsolidated, undrained test, or let me get this back. Yeah. In an unconsolidated, undrained test, basically, you have, this is your soil sample. And here you have a drainage valve to allow drainage. In an unconsolidated, undrained test, this valve will be closed. So it will be closed during the application of sigma 3, and it will be also closed during the shearing phase, or the phase where you apply the major principal stress, sigma 1. And if we would take a look at our failure envelope, or Mohr circle would look something like this. And you can see that these are not effective stresses, these are total stresses. And you can measure pore water pressures, but we'll just talk about a case where you're not measuring pore water pressures and you don't want to derive an effective stress parameters. And let's say you would run the same exact test on the same exact sample at a higher confining stress. What would happen is it would just shift to the right. So this would be your sigma 3, and this would be your major principal stress. So basically what I guess I'm trying to show you is these would be equal, and this is the undrained shear strength, or SU, because in an unconsolidated, undrained test, you don't allow consolidation, so the sample does not gain strength. Now, if we would, for example, take a look at, let's say, a consolidated drain test. So again, during the first phase of your test, the application of this sigma 3, this valve would be open. Okay? And then during the application of your major principal stress, this valve will also be open. So, and you also have a pore water pressure measurement during both phases. So basically what you have in a consolidated drain test is something that looks like this. And notice how these two parameters will be effective stress parameters. And if we would, for example, run another consolidated drain test on another sample with a higher sigma 3, then your sample would be something like, let's say, I don't know, this. This would be your sigma 3. This would be your sigma 1. So this would be your sigma 3. Or let me fix it up. So it would be this is your sigma 3, this is your sigma 1, and if you would run it at a higher consolidation stress in the consolidation phase, it would look something like this. So I guess what I'm trying to say is because you allowed consolidation, you have a gain in strength, and this would be your failure envelope, and phi would be an effective stress parameter. And that's for a consolidated drain test. Now, I guess for the consolidated, let's say, undrained test, oops, oops, oops. Uh, your drainage valve, because you see it's a consolidated, will be open during the application of sigma 3. And once you finish applying the consolidation pressures, what you would do is you would close this valve in phase 2. In phase 2. So it's undrained. And so you will have pore pressures develop, and you will have pore water pressure measurements here. And if we would take a look at the Mohr-Coulomb failure for this one, what would happen is, what would happen is you would have a failure line that looks like this. But you have a pore water pressure measurement in this case, right? So what you're going to do? Simple. You're going to shift this circle to the right. Oh man, horrible. Okay, you would shift it to the right. So this is your sigma 3, and that would be by the change in pore water pressure. And so even though the shearing phase is undrained, because we have a pore water pressure measurement, we can determine our effective stress parameters. And that's what you would get. So this is not, this dotted circle right here is not another test. It's just the same test. When you have the pore water pressure measurement, you simply shift that to the right, and you can have an effective stress parameter. And that's for a consolidated undrained test. And basically, in a consolidated undrained test, what's going on is that, you know, there's a negative pore water pressure is being generated because the soil tends to want to pull in water. And so that's suction, it's negative pore water pressure, and that's why you shift it to the right. Now, if we talk about a triaxial test equipment itself in a more detailed view, here you have your soil sample, and it will be inside this chamber. It will be covered by a latex membrane. And here you have a pressure gauge measuring the pressure inside the cell of the de-aired water. This is your sample. The purpose of the latex membrane is you don't want the water in the sample to mix with the water in your sample. I mean, you don't want the water in the chamber to mix with your water in your sample. So you want to have a separation between them. That's why you have that latex membrane. And I think I have this video from Kansas University, and I think it would be a good video just to point out a few things. I mean, so let me point out, this is your soil sample, and at the start of the test, you would measure the length of this sample and the diameter of this sample. You would take 3 measurements and average them out, and same with length. You would measure length from here, length from this side, and length from the back. And that way you can calculate, for example, if you want the water content, in measuring the dimensions, you can calculate the strain change before and after the test. And you can also take from your soil sample, originally you take a moisture content measurement. Basically, you take a sample and you put that sample in an oven. And with that, you can determine the water content before the test and the water content after the test. And this is just simply, you will place the latex membrane on this device right here, and that will allow you to put your soil sample in. And so this latex membrane will cover your soil sample. Here you have all the drainage, different drainage valves, depending on what you want to measure. This is a relief valve, and this is the piston that applies the load. This is the chamber itself. The bottom of the chamber is going to be sealed off with like a vacuum seal. And with that, what you can do is you can begin the test. So this is two will be one on top and one on the bottom, and it's kind of just like a plastic plastic cylinder, I guess, and you can put the soil sample on top and it'll be straight, so you can apply the load uniformly to the sample. And this is the top, and you can see it has a small circle inside of it, and that's where the piston will go to apply that major principal stress. And with that, you see your drainage valves. One is at the bottom of the sample, and you have a drainage valve for the cell, and you have other valves that pressurize the cell itself. And basically here, they just remove it. And what you would have, actually, you can have two O-rings on the bottom, not just one. Here, two, and two on the top as well, just to make sure everything is sealed off. Then they put this cap, and they'll put a ring, or they should put a ring right on top of this one as well. And after that, this is the load cell, and here you have a transducer, and you can measure the strain rate and all the different changes in your sample. And these are the bolts that are going to seal this chamber, because you remember you're going to pressurize it. Now they're trying to apply this water. Again, this is a de-aired water. So this water, for example, I don't think is it shown here? No. So this water would come from a chamber right up top, which has a water that has been de-aired. And this is just their particular software that they are using. This is a very helpful video. Once school opens up, we're gonna make something like this. And now, if we would go back, if we would go back to the test itself, basically, again, we talked about the cell, the chamber, the loading frame, and here is a control panel. So it's different than the video we've seen. Here it's more manual, so you have to turn these gauges when you want to pressurize. And that's something that I just remembered, actually. Basically, before the start of a triaxial test, what you want to do is you want to be at 100% saturation or very close to it. And there's different ways to achieve that. There's around 5 different ways to achieve that, but I'll just mention briefly how you would be able to do that. So basically, you want to raise the pore water pressures inside the sample, and at the same time, you're increasing the confining the stresses around the sample at a constant rate. So you kind of like dissolve all the air inside the sample, and you try to get a B value to 0.98. And what a B value is, it's a coefficient or pore water pressure coefficient. And what this pore water pressure coefficient is equal to, it's equal to the change in pore water pressure divided by the change in the minor principal stress. And that's equal to B. And you want to achieve that because, you know, it's hard when you have air to measure the change in pressures of the air inside the sample, even though it's done for research purposes. for all commercial tests is basically you try to get your sample to close enough to 100% saturation, and then you would do the test. And if you don't get if you don't have your sample at 100% saturation, what would happen if we just look at this from a UU test result? This at the beginning, this failure line would be curved, and then it would be straight. So if you have this kind of situation, then it means you have you are partially saturated, you're not fully saturated. And again, this would be your shear strength parameter. This is your phi equals 0 condition, and that's the condition that you get from an undrained, unconsolidated, undrained test. This is here it says short-term test. So I don't want to get too much detail because this is an undergraduate class, but I'll just say that short-term test, basically, if you remember when we talked about drained versus undrained conditions, you have in a short term, let's say you have some cohesive soil and you have your foundation on top of cohesive soils. At the beginning of the construction, what is short term, start of the construction, your soil is going to behave in an undrained fashion, meaning you're not going to have those pore water pressures dissipate over time. So if you're looking for a strength at short term, then you're looking at an undrained test, unconsolidated, undrained. Long term, remember, we talked about this in consolidation lab, you will have the pore water pressures leave the sample. You will have an increase in effective stress because all that pore water pressure, remember, effective stress is total stress minus pore water pressures. So you would have a drain condition, or meaning that the drainage has been done, or let me rephrase, a drained condition meaning as soon as you apply the load, the pore water pressures dissipate or leave the sample. That's a drained condition. Undrained condition meaning that there's a lag time, or with the application of a vertical effective stress, you don't have water leaving the sample as soon or as with the rate that you're applying the stress with. Now, if we would again go back to this is the Mohr-Coulomb failure criteria that we talked about. This part is where the soil derives its strength from cohesion. This is cohesion, and this is internal angle of friction. And we've mentioned this, I think, a couple of times. So cohesion, this is C plus tan phi. And this is the frictional resistance between the particles, the soil particles themselves. And that's the shear strength of the soil. This we've mentioned, it's resisting to shearing stresses. We mentioned that all these values are used in ladder pressures calculations, slope stability, bearing capacity calculations. That's why we need all these shear strength values at failure.